Hey everyone, welcome back to another video by Camroom 5. In today's video, we're going to be talking about the conditions for ideal gas behavior. Because in the previous video, why do I do this? Let me change that, yeah. So in previous video, we had been talking about the ideal gases. And I think it's a good time to talk about the conditions, which include high temperature and low pressure. So these are the two conditions where any gas is likely to behave ideally. For example, at high temperature, particles of the gas, when they absorb heat energy and their temperature increases, they actually absorb this heat energy, and overcome their intermolecular forces, or you can call them the van der Waals forces. So as a result, there is negligible forces between them. And that was one of the conditions and that was one of the criteria for ideal gas, right? Another scenario is that at very low pressures, the gases expand. And when I say expand, actually the overall gas volume increases. So the volume of the particles becomes negligible compared to the overall volume of the container. So particle volume itself becomes literally negligible compared to the container volume, and that was another attribute of any ideal gas. Now moving on, for the general gas equation, PV should be equal to nRT. For 1 mole of any ideal gas, the small n should be equal to 1. So it becomes PV is equals to RT. If I take a ratio of PV divided by RT, it should be equal to 1 because they are literally the same values. And that is under all conditions for an ideal gas. So for an ideal gas, no matter what the temperature or pressure is, the PV should be equal to RT and the ratio is 1. So let's take pressure in pascals on the x-axis and let's take the ratio, which is PV divided by RT on the y-axis. It's a constant value 1, so for an ideal gas, no matter what's the pressure, it should give you a constant horizontal line despite whether it's low pressure or high pressure. But if it's a real gas, which is a non-ideal gas, the value should be more than 1, less than 1, initially more than 1, then goes less than 1, whatever. The purple lines show that it is not equal to 1. It shows that it is a non-ideal gas. The value of the ratio, the deviation of the PV divided by RT ratio from 1 shows, it means that it's a non-ideal gas. And that justifies that all the gases in nature do not behave ideally. Now let's jump to some past paper questions where we will be using the general gas equation. For example, when we look at this question, it says a 10 centimeter cube bubble of an ideal gas is formed on the seabed where it's at a pressure of 20 kilopascal. Just below the sea surface, the pressure is 101 kilopascal and the temperature is the same. What's the volume of the bubble? So we use the Boyle's law, which connects the volume value with the pressure value, and it says pressure is inversely related to volume. We know that pressure and volume product in first case is equal to the pressure and volume in the second case product. So 20 kilopascal was the pressure in first case, 10 centimeter cube was the volume. If 101 kilopascal is the pressure in second case, what's the volume? We can neglect the kilopascal value, kilo, because it's same on both sides. And volume simply turns out to be 200 centimeter cube, so C is the answer. Let's look at this question where it says 0.96 gram of oxygen gas, which is the mass, so it is the mass of oxygen gas, is contained in a glass vessel of volume 7 exponent minus 3 meter cube. So we have the volume and temperature is 30 degrees Celsius. We convert it into Kelvin by adding 273, so it becomes 303 Kelvin. They're asking us for the pressure. So it's very simple. PV is equal to nRT. Pressure is unknown, we put the volume value, which is 7 exponent minus 3. We need to find the moles, so mole is equal to 0.96 over 32 because it is O2 gas. 8.314 times temperature, which is 303 Kelvin, divided by the value of volume in meter cube. So 7.0 exponent minus 3 meter cube. We simply solve it and we get to know, we need to have a calculator around us. Moles times 8.314 times 303 divided by 7 exponent minus 3. Yeah, so it turns out to be 10.8 kilopascal. Now let's jump to another question where it says the volume of a sample of methane is measured at a temperature of 60 Celsius. I got to convert it into Kelvin, and the pressure of 103 kilopascal, the volume is 5.37 exponent minus 3. Let's convert the degree Celsius into Kelvin because Kelvin is the SI unit. I will add 273, so it turns out to be 333 Kelvin. The pressure should be taken as 103 exponent 3 Pascal because we need to remove the kilo from it. The volume is already in the SI unit. What's the mass of the sample of methane? So we need to find the moles. Mole is equal to PV divided by RT. So number of mole is 103 exponent 3 Pascal times 5.37 exponent minus 3 divided by 8.314, which is R, times 333 Kelvin. When I solve it, I get to know that the number of mole is equals to 1.997 exponent minus 1, which is 0.1997. Mass can be easily found out by doing moles times MR for whichever gas you are dealing with, so that's methane. So moles times 16 turns out to be 3.2 grams. Let's jump on another question. Which diagram shows the correct graph of PV against number of mole for an ideal gas? Now, we need to find a relationship between PV and number of mole, and let's begin our discussion at constant temperature using the general gas equation. So PV is equal to nRT. If we know that R and T are constant and we take a ratio of PV over N, it gives you RT, which is a constant value. So R is a constant and T is also a constant in my case. So the ratio is basically proportional to R. And we know one thing for sure, that if we take x-axis to be moles and PV should be taken as y-axis, the slope of this graph will give you the value of R. So D is the right answer, because if number of mole increase, PV will also increase, and that will give you a relationship with R. C is wrong because the gradient is 0 for this graph, while in B it's a negative gradient, which is never true. If you increase moles, the volume has to increase. And A is wrong because at 0 mole, how can it have any volume at all? Because at 0 mole, 0 volume. So D for doctor is the right answer. Now moving on, let's pick one more question and let's figure out. Let me search for it. Yeah. The gas loss can be summarized in the ideal gas equation when an evacuated tube of volume has been given. So 400 cm cube should be converted into meter cube. You should know that centimeter cube with exponent minus 6 becomes meter cube. So you need to make sure that your values are in meter cube rather than any other unit. Then they're giving us temperature in Kelvin and pressure is kilopascal. So I will add exponent 3 because I need to use pascals. In order to remove the kilo, I add exponent 3. Assume the gas behaves as an ideal gas. I have the mass with me. So PV is equal to nRT. I need to find the MR of the gas because I need to find the identity. So PV divided by RT would give me the number of mole. So I put these values here. 8.314 is the value of R. Temperature is 300 Kelvin. The number of mole can be found out. So 101 and 400, exponent 6 cancels exponent 3 and I get exponent 3 as remaining divided by 8.314 Okay, so number of mole is equal to, in my case, 1.603 exponent minus 2. Now these are the moles and I have the mass with me, so mR is equals to mass divided by mole. When I have the value of mass with me, which is which is 0.65 grams, and I have the value of mole also, I get the mR, which is 40.53 gram per mole. So this turns out to be argon because argon has an mR of 40 units. Let's do this one. What are the basic assumptions of the kinetic theory as applied to an ideal gas? Gas particles are in continuous random motion. True. Gas particles experience no intermolecular forces. The volume of each gas particle is 0. All three are correct. So that is a revision for us for ideal gas behavior also. Now this question says, which diagram correctly describes the behavior of a fixed mass of an ideal gas? Temperature is measured in Kelvin. So fixed mass means fixed moles. Option A seems correct because that's literally Charles' law. If you increase the temperature, the volume also increases. Option B is wrong because volume and pressure were supposed to be inversely related, not directly related. Option C is wrong because we know that the product of PV is equal to nRT. So if volume goes up, pressure goes down, and PV is literally a constant, which is nRT. So option C is wrong. Why is the line increasing? Why is it not constant? And when we talk about option D, it is also wrong because we know that PV is again a product constant. The last question says, at which temperature and pressure would the behavior of chlorine become most ideal? So most ideal means high temperature and very low pressure. So I will look for the highest temperature and I will look for the lowest pressure. So option C for cat makes the most sense because higher temperature is there and lower pressure. I hope these ideas are clear to you guys. Stay tuned.